A pilot drops a bottle out of an airplane. The plane from which the bottle was dropped was flying at a height of 500 meters, and the bottle lands 400 meters horizontally from the initial dropping point. There are 5 parts to this problem. Part A. Draw a force diagram for the bottle after it has been thrown, but before it strikes the ground. Assume the air resistance is negligible for the bottle. B. Write an equation for all the vertical forces acting on the bottle. What is the vertical acceleration? C. Write an equation for all the horizontal forces acting on the bottle. What is the horizontal acceleration? D. How long is the bottle in the air before it lands on the ground? E. How fast was the plane flying when the bottle was released? Parts A, B, and C go hand in hand. Every time we draw a force diagram, part A, we should be writing the sum of the force equations for the horizontal and vertical forces acting on the bottle, parts C and B respectively. So when the bottle is in the air, we are going to be drawing a force diagram for the bottle. The first force we draw every single time ever is the force of gravity. That is that interaction between the Earth's gravitational field and the object, in this case, the object being the bottle. While it is in the air, after it has left the plane, but before it has struck the ground, the only other thing interacting with the bottle would be the air. However, we are told that the air resistance is negligible for the bottle. What that means is there are no other relevant forces acting on the bottle other than the interaction between the Earth's gravitational field and the bottle itself. So this is our force diagram for the bottle while it is behaving as a projectile. The sum of the forces horizontally, part C, would be nothing. There are no forces horizontally. So sigma Fx is equal to 0 newtons. We can write sigma F as mass times acceleration, which would be equal to 0 newtons. Because the bottle has some mass, in order for the mass times our acceleration to equal 0, that means the acceleration horizontally needs to be 0 meters per square second. Now for the sum of the forces vertically, part B. We have one force, the force of gravity. We can rewrite sigma Fy as ma, and we can rewrite Fg as mg. The masses cancel out, so the mass of the bottle is irrelevant when the only force acting on the bottle is the force of gravity. As such, our acceleration is equal to the gravitational acceleration of an object near the surface of the Earth. That value of 9.8 meters per second squared. This is our force diagram, our summation equations, and our accelerations for an object behaving like a projectile, where our air resistance is negligible. For part D, when we're trying to determine how long is the bottle in the air for before it lands on the ground, this is where we're going to need to use our horizontal and or vertical variables and our kinematic equations. Now I'm going to go through the list and populate them based on the starting positions, final positions, starting velocities, final velocities, and time, given the variables in the problem, as well as some assumptions that we can make. Now, in the previous parts, B and C, we were able to show what the horizontal and vertical acceleration should be. In fact, for projectile motion, we can make the assumption that our horizontal acceleration will always be 0, and our vertical acceleration will always be 9.8 meters per second squared. And I'm just going to kind of default to saying down is our negative direction, so my vertical acceleration will always be negative 9.8 meters per second squared. The rest of these variables will come from the problem. Now, for the starting position horizontally, we don't know at what horizontal position the plane dropped the bottle. However, we're just going to define wherever it was when the bottle was dropped is going to be our horizontal position of 0. So our starting horizontal position will be 0 meters. And we are told the bottle lands 400 meters horizontally from the initial dropping point. So that would make our final horizontal position 400 meters. We are not told our initial horizontal velocity. And because our acceleration horizontally is 0, we also do not know our final horizontal velocity. These two velocities should be the same for the horizontal motion because the acceleration is 0. Now, when it comes time for our vertical variables, we know that the bottle was dropped at a height of 500 meters. That would be our starting vertical position. And the final vertical position would be the height of the ground, which would be 0 meters. Now, we can make the assumption that because this plane was flying above the ground, we're assuming it's flying horizontally. If that assumption is true, that means the starting vertical velocity would be 0. This bottle would be horizontally launched. And we don't know the speed of the bottle when it strikes the ground, or rather the instant before it strikes the ground. For part D, we're trying to figure out how long the bottle is in the air for. So we're going to be solving for our time. Now, our time is going to be the variable that connects our horizontal and vertical variables together. Because other than time, our horizontal and vertical motion are independent of one another. Now, to solve for our time, we're going to need to choose a list of variables that has enough information for us to solve for the time. Our vertical list has more variables for us to work with in a way that allows us to determine the time. Using this equation, we know all of the variables except for our time, so we can solve for our time from this. We know our final position, our starting position, our starting velocity, looking for our time. We know the number 1/2, we know our acceleration, and we're looking for t. So I plug in the values that I know. 0 meters for our final position, 500 meters for the starting position, 0 meters per second for the starting velocity, and then negative 9.8 for the acceleration. Simplifying this down and subtracting 500 meters from both sides, I can say that negative 500 meters is equal to negative 4.9 meters per second squared times t squared. The way that I did that was I subtracted 500 meters from both sides, and then because my starting velocity is 0, that middle term would just go away. And then finally, 1/2 times negative 9.8 is negative 4.9. So to get t squared by itself, I divide both sides by negative 4.9, which would give me positive 102 seconds squared is equal to time squared. To figure out the actual time, I just take the square root of both sides. So the amount of time the bottle is in the air for before it strikes the ground is 10.1 seconds. Now, to finally answer part E, how fast was the plane flying when the bottle was released? We are making the assumption that the plane is flying perfectly horizontally. So we know the plane's vertical velocity would be 0. So we need to solve for the plane's horizontal velocity. Now we know that the plane's horizontal velocity should be the same as the bottle's initial horizontal velocity. So we are going to solve for that using the time that we calculated in the previous part. We can use the horizontal variant of that equation we used in part D. We know the final position, we know the starting position, we're looking for the starting velocity, we know the time, we know the horizontal acceleration, and once again, we know the time, and we can square it. Plugging in the values that we know, 400 meters for the final position, 0 meters for the initial. Leaving the variable of the initial velocity by itself, plugging in the 10.1 seconds for the time, the 0 for the acceleration. We can simplify this down to show that 400 meters is equal to our initial horizontal velocity times 10.1 seconds. Dividing both sides by 10.1 seconds, we can say that the initial velocity of the bottle horizontally is 39.6 meters per second, and we can make the assumption that that should be the speed of the plane as well.